So good morning. Good morning, AGU, I should say. My name is Paul Newman. I'm from the NASA Goddard Space Flight Center. And following on from Michelle's talk about asteroids and planetary defense, I'm going to talk about the Earth's natural planetary defense. And that's stratospheric ozone. Stratospheric ozone is a gas, 3 oxygen atoms bound together. And atmospheric ozone screens solar ultraviolet radiation. The ultraviolet that is energetic enough to break the bonds of biologically active molecules, like carbohydrates and sugars. In fact, the most important being DNA in our bodies. So UV causes things like sunburn. It can lead to skin cancer and cataracts, but it also can damage plants. So I'm going to start off by showing you a picture of what we call the Antarctic ozone hole. And this is a massive depletion of ozone over Antarctica. You can see this big purple color here. That is the total amount of ozone between the space and the surface. And we measure it in what we call Dobson units. So purple shows very low values of ozone, and red shows very high ozone. Now, around the green is about 300 Dobson units. It could bring all the ozone down to the surface. That would form a layer of ozone, a gaseous layer, 3 millimeters thick. That's the thickness of 2 pennies stacked on top of one another. Now, over Antarctica here during the ozone hole, it's the thickness of a dime. That's how much depletion we've had. We've gone from about the thickness of 2 pennies of ozone to the thickness of a dime. Now, that's enough to screen 90% of all the UV coming in from the sun. When you get to the really hard radiation, it screens 100% of it. So let's go to the next slide. Okay, so what I was just showing, and I think this is, and it should start running. This shows a series, we'll get back to that. Okay, so down here you can see the dates, and there's various years here, 1979, 80, and 1981. Now on the bottom is 2015, 2016, and 2017. You can see the dates rolling by. This is August. If you look up here at this 1979, you can see this is every day. We map ozone globally every day around the planet. So we cover both the Arctic and the Antarctic. So you can see by the time you get to early October, compared to those early years, you have a lot of depletion. So the ozone hole developed back in the 1970s and early 80s, and it got really deep as we got to the 1990s. Now, it's a seasonal phenomena, so all the depletion occurs in the July, August, September period, and it reaches its deepest levels in early October. And then what happens is it kind of breaks up, and it mixes this low ozone air out into the mid-latitudes. It lowers ozone everywhere across the southern hemisphere. So the ozone hole depletes ozone even over places like Australia. So you can see Australia is way down here. But when the ozone hole breaks up and mixes this low depleted area out over the mid-latitudes, it lowers ozone over Antarctica populated regions. So why don't we go to the next slide? So this is just to give you an idea of what's happening with the ozone. And so what we have here is we show the area of the ozone hole up in the top here. And that's basically the area outlined in the blue. So where you see you can just total up the area. And that's the ozone hole area. Now, so this is this last year and shows the daily values. If you average that, that's what you get up here. You get this plot here showing the average area of the ozone hole for each year. All right? And so you can see 2017 at the very end. It's a little bit less than what we've seen historically. So it's but you can see if you go all the way back to 1979, it was near zero. In fact, before 1979, it was zero. Now, if you actually look in the middle here, you can pick off the lowest value of ozone. We average those together, and that's this graph right here. This shows us the ozone minimum. So you can see, again, falling as you went into the 1990s. Now, the good story, and I'm going to get to this in a second, is that if you look closely at this graph, you can kind of see it's sloping upward. And so ozone was depleted, and now it's starting to increase. So we kind of have a good story here. And we're going to get to that in a second. Why don't we go to the next one? Okay, so now this shows the values during October. So October 1st for all these 9 years. We have actually every year since 1979. but we're only showing these example years. Here's 79, 80, 81. And you can see ozone gets down to something like, the scale isn't quite on here, but about 280 Dobson units or so. And you can see in the different years how it gets lower and lower and lower. So if you compare 1979 with 2015, you can see the big difference in the evolution of the ozone hole. So let's go to the next one. So now what's causing this? What's causing ozone to go down over Antarctica? It comes from some natural compounds and some man-made compounds. There's gases like methyl bromide, methyl chloride. This is a man-made gas, carbon tetrachloride. CFC11 is a man-made, chlorofluorocarbon 11 is a man-made gas. CFC12 is a man-made gas. These ones out here called halons, these were used as fire extinguishing agents. In fact, if you go to the airports now, you look out on the tarmac, you'll still see these big canisters that they use for fire extinguishing. Those contain halons. Halons contain bromine, and the CFCs contain chlorine. And it's that chlorine and bromine will attack ozone molecules. One chlorine atom can destroy, once it gets into the stratosphere, can destroy thousands of ozone molecules. So you can see as we were using these as we go through the 1960s, 70s, and 80s, it was growing. These levels of these compounds were going up and up and up. In 1987, they signed an agreement called the Montreal Protocol. So this was recognized back in 1974 that there could be ozone depletion. Two gentlemen, Sherry Rowland and Mario Molina, published a paper suggesting that these chlorofluorocarbons, they're very long-lived. Once they get into the stratosphere, could break down, release their chlorine and bromine, and that would attack ozone. So fortunately, the Montreal Protocol was signed in, you can see the growth here again. The Montreal Protocol, so they first announced this study in 1974. In 1987, they agreed to the Montreal Protocol. That's this nice vertical line there. And then you can see it peaked in about the year 1996 or so, and now the levels of these gases are falling. So that's a great story. The parties, the nations of the world recognized that the ozone layer was threatened, our natural defense, and they had to do something about it. So they negotiated the Montreal Protocol, and the good news now is the levels of these ozone-depleting gases are now starting to fall in our atmosphere. Next. So this is a model projection. Luke Oman, who's standing right here, he ran this model projection. This shows a variety of years. Here's the ozone hole averaged for October in 1971, 2017. This is an actual observation. These two are observations. This is the model, 2041 and 2065. So projecting out the average October value that we see, the white points are from satellite, the red points are from the model. So the model, as these chlorofluorocarbons decline, the levels of ozone begin to increase. And you can see there's year-to-year variations. But you can see you go back to this 1980 level when we first began to see the ozone hole sometime in around 2060. So the model is telling us that, in fact, ozone ought to be getting better over Antarctica. Here we are in 2017. And if you look at this point, so you can kind of see this upward fading of ozone. So it looks like there are hints now that ozone is getting better over Antarctica. So next slide. So what if we had done nothing? What if the Montreal Protocol had never been signed? And I'm going to show you, this is the Montreal Protocol world where ozone-depleting substances continue to go down. This is what we call the world avoided, in which there was no Montreal Protocol. You can see the levels of chlorine in the atmosphere between this world and that world. So here's ozone, and you can see the formation of the ozone. It's a seasonal phenomenon, so you can see it bump up. You get out to about 2025, and you'll now see an Arctic ozone hole start forming. If you look at the expected world, you don't see that. You see high ozone over the Arctic. And you can see ozone almost everywhere is going down in this world avoided. So by the time you get out to 2065, 2/3 of the ozone layer is gone. 2/3 of it, because of those growing levels of chlorine. Now, if you look at that, it says Cl parts, ppb, parts per billion. If you take 1 billion molecules, it only takes about 50 of them in a parcel of air to destroy the ozone layer. So it's not a lot. This world was certainly possible if nothing had been done. Now, what does that mean? So for us here in the New Orleans area in the mid-July, it probably means UV index. Everybody knows, I think everybody knows what a UV index is. Typically in the middle of summer, it gets up to 10, 11, 12. In the world avoided, it gets up to something like 30s to 40s here in the US. Now, what that means is that your UV exposure is, in the middle of summer, is 3 to 4 to 5 times larger than it would have been naturally. That means that a guy like me going outside in the summertime, I can probably go outside for 20 minutes, just enough time to mow the lawn without getting a sunburn. In that world, I could go out for about 5 minutes without getting a sunburn. But worse than that, it's the impact on crops, okay? Because of the increased UV levels, crop yields are going to fall in this world. You can imagine how bad that would be for the US. But think of all these densely populated countries like China, India, the impact of huge crop reductions in those parts of the world. So I like to say that I think that the parties, the nations of the world actually did a great thing by regulating these ozone depleting substances. Okay, next. So this is another movie that we made. This is, again, the Ozone Hole for this year. And it's actually kind of fun to watch. You can see the date evolving along the bottom here. So you can see August 15th. And you can see the motions of, these are all various weather systems. And you can see their general motion around here. There's a big, strong jet that goes around like this. Again, this is low ozone. This is higher ozone. And here's the scale of Dobson units. Remember, this is about a thickness of a dime. This is about the thickness of 2 pennies stacked on one another. So some of these red areas, there's a lot of ozone there. Okay, why don't we go to the next one? So what I'm going to show you now is that's the same movie, same ozone over here. And over on the right is the UV index. So we can take this ozone and we can compute a UV index. Now this is just for overhead sun. So this is actually a computation, but we can compare this to real data and we can actually show that this works pretty well as long as it's clear sky. So now as you watch this, remember the sun is pretty low in August and it's starting to rise over Antarctica. Now if you look closely, you can see there's pretty high UV index in the tropics. Okay, you expect that. The sun is directly overhead. There's not a lot of ozone out there. You get a really, really high UV index. Now is the sun, and again, the sun is going up. So you can see the UV index is brightening. It's going to higher and higher values as you go towards, as the sun continues to go up. So the sun is getting higher in the sky. And now you can see the motion of the ozone, as the ozone hole is moving around, you begin to see these very, very large UVs. See the pop-up of the high UV index as it's going around. So you can actually, we have stations on the ground that measure UV, and you can actually show these like this one right here, as the ozone hole is swinging around. You can see how it's really kind of mobile, like an amoeba, and you can see the very high ozone events popping up. Now those are totally not natural, okay? And that UV getting to the surface impacts all sorts of phytoplankton, crop yields, and so forth. Now you can really see as the sun's very high in the southern hemisphere. They're really high. These are natural UV levels, but these other UV levels that we see down over Antarctica are not. So with that, I'm going to close here, repeat this movie, and just to point out that we measure ozone every day. These are dedicated satellites between NASA and NOAA. We compute things like we can measure and compute the UV index to show how crops and people are being affected. And just to point out that the Montreal Protocol did a really great thing in regulating ozone depleting substances. So thank you for your attention. I can take a question or two.